When we did stoichiometry, we didn't really care about the state of the matter. We just converted everything into grams. But when we have something dissolved in a liquid, the grams become really difficult to deal with. It becomes difficult to deal with a mass. If I've got a solution of hydrochloric acid, it becomes very difficult to tell what's the mass of HCl in this. That doesn't really tell me much about what is contained in this solution. Because I could have 10 grams of HCl dissolved in 1 liter of water. That might be a bit. Or I could have it dissolved in 100 liters of water. That's going to have a lot of impact on how quickly something reacts or really how much HCl I'm going to have. So we need a better way to look at this. And for that, we use the concept of concentration. We're going to use this equation, and this is going to come up a lot, especially when we look at acids and bases. So you should commit this equation to memory. You've got concentration, number of moles, volume. So N, number of moles. C is concentration. And V is going to be volume. Concentration is measured in a concept called molarity. So when we say molarity, what we mean is the number of moles dissolved in a volume of a solution. Okay, so molarity, we can also say molar. So if I've got a stock solution of hydrochloric acid, if I've got this in the acid cabinet, it's going to be a 12 molar solution of HCl. That tells me the concentration of that hydrochloric acid. This is a very high concentration. This could do a lot of damage if it's spilled. So we generally don't work with this concentration. We usually want to work with something that's more in the line of 2 molar HCl. If we need to work with some strong enough acid to do some busy work, we're going to work with 2 molar HCl. But in the classroom, if we needed to do something like use the acid as an electrolyte, we might want to use something like 0.02 molar HCl, because it would be a strong enough acid that it would work as an electrolyte, but not so strong that it would dissolve our metals. Okay? If we're doing something like a titration, just to measure the concentration of the acid or a base, which we'll do in the next unit, we might want to use a very low concentration because we're going to use an indicator that's going to be really sensitive to the concentration. So we might use an even smaller concentration. So we need to be able to figure out in all of these, how many moles am I going to have? So let's look at that. Let's say I've got HCl. We'll keep using that as our acid. Let's say I've got 4 moles and it's dissolved in 10 liters. What would be the molarity of that? Well, that's just going to be number of moles divided by volume equals concentration. So that's going to be 4 divided by 10 equals 0.4 molar. All right, simple enough. Now, how about if I have 10 moles dissolved in 10 milliliters? What would that be? Well, now this is where it gets tricky. Often we measure things in milliliters, but this equation officially uses liters for volume. This volume needs to be in liters in order for us to use it. So if I wanted to put that into the same equation, I would say 10 moles over 10 milliliters. How many milliliters are in a liter? 1,000. So I need to take 10 divided by 1,000 to get into liters. So that's going to be 0.01. So I would say 10 divided by 0.01. Ooh, that's going to be a lot. So 0.01, 10 divided by 0.01, that should be 1,000 molar. That would be an incredible high concentration. So we wouldn't want that. Let's do some more. Let's say I've got a 4 molar solution of HCl, and I've got 100 milliliters of it. How many moles of that do I have? Well, it's going to use that same equation. It's just this time I'm missing the moles. So I'm going to say my concentration is 4 equals N over 0.1. So I can take the 0.1 times the 4. So I go 4 times 0.1, just rearrange that equation to give me N. 4 times 0.1 is going to be 0.4. So I'd have 0.4 moles. There we go. And so I've got a solution of NaCl. It's a 3 molar solution, and I've got 475 milliliters of it. How many moles is that going to be? Well, 3 molar solution equals number of moles divided by volume, and that's going to be 0.475 liters. So we can take 3 times 0.475. That'll give us 1.425, 1.425 moles. Now let's try something a little more complicated. Let's say I've got a solution. Let's go back to the acid. I've got a 2 molar solution of HCl, and I know I need 4 moles in order to complete a reaction. How many liters am I going to want to get of that 2 molar solution? Well, I'm going to plug those values in. So 2 molar equals 4 moles divided by my volume. Now to rearrange this equation, first I need to get volume away from the bottom. I don't want that in my denominator. So I'm going to multiply both sides by the volume. It's just the algebra here. I'm going to get 2 times V equals 4. And now I need to get the volume alone, so I divide it by 2. And so I get V equals 4 over 2, which means V equals 2. So that'd be 2 liters. I would need 2 liters of 2 molar HCl to get 4 moles out of that. Let's try one more like that. So let's say I've got a 0.25 molar solution of iron 2 chloride, and I need to get 0.6 moles out of that. So I'm going to set that equation up. I've got concentration equals number of moles over volume. This should be committed to memory. The concentration is 0.25 equals 0.6 divided by volume. So now volume goes to the other side. 0.25 times V equals 0.6. Now divide by 0.25, and I get V equals 0.6 divided by 0.25. Let's run that calculation. 2.4. And so our volume would be 2.4 liters. Great. So we should be able to calculate the concentrations going back and forth from number of moles to volume to concentration over and over again. This should be second nature because we are going to be using this in stoichiometry in the future.